Okay, so what if one of the most fundamental rules of the universe, something taught in every single physics class, isn't actually a rule at all? What if it's more like an illusion, an echo of a reality that's way deeper and stranger than we thought? Well, today, we're diving into a fascinating new paper that suggests exactly that, proposing that we can, believe it or not, literally hear the shape of an atom.
So here's how we're going to break this all down. We'll start with the quantum mystery that's been bugging physicists for about a century now. Then we'll get into this wild new idea about the sound of empty space. We'll use a pretty amazing analogy that involves a concert hall, and then we'll see if this new model actually holds up against the hard data we have for the hydrogen atom. And finally, we'll ask the big question. What does it all mean if our universe is built on emergence?
All right, first up, the quantum rulebook. To really get how revolutionary this new idea is, we first have to wrap our heads around the very specific, very old rule that it's trying to break.
And that rule really boils down to this one question. Why are atoms so darn picky? You see, an electron orbiting an atom can only have very specific, discrete energy levels. It can be here, or it can be here, but it is absolutely positively forbidden from existing anywhere in between. It's kind of like a staircase, where you can only stand on the steps. You can never, ever float between them. But why? Well, for about 100 years, the standard answer from quantum mechanics has basically been a shrug, because that's just how it is. Those are the rules. This whole quantization property is treated as a fundamental postulate of the universe. It's not really explained, it's just accepted as a brute fact of reality. Well, that might be about to change.
So, let's move on and see how a new perspective completely changes the picture. Let's talk about the sound of the vacuum.
This is where the authors of this paper ask a really profound question. What if quantization isn't some fundamental top-down law that's written into the fabric of the cosmos? What if it's an emergent property, something that just arises naturally from a deeper and maybe even simpler reality? To get there, they introduce this idea they call the dynamic vacuum. The whole point is to stop thinking of the vacuum of space as this empty, passive stage where all the action of physics happens. Instead, they model it as an active, almost fluid-like medium, a participant in the play itself. And this is a really huge shift in thinking. On the left, you've got the standard view. Space is just the container. It's passive. But in this dynamic vacuum model on the right, the vacuum is part of the machinery. It can be bent, it can be shaped, it can be vibrated, and those vibrations, as we're about to see, are the key to everything. Now, to make this all feel a bit less abstract, the paper uses this incredible acoustic analogy. I want you to think of an atom as its own little tiny concert hall. Okay, so here's how it works. Step 1, the dynamic vacuum is like the air inside that concert hall. Step 2, a particle, like a proton, doesn't just sit there. It imprints the vacuum around it. It changes the local properties, basically creating the walls and the unique shape of that concert hall. Step 3, now, any given hall shape can't support just any sound, right? It has specific, stable, resonant frequencies, notes that just ring out perfectly clear. And step 4, and this is the big leap, those stable resonances, those allowed notes of the vacuum, are the allowed energy levels and orbitals of the electron. They're not some magic rule, they are just the natural acoustics of space itself. And that brings us to the moment of truth, the hydrogen blueprint. I mean, it's a beautiful idea, right? A powerful analogy. But does this acoustic model actually describe the real world? Well, the simplest testing ground for any new atomic theory is always the humble hydrogen atom.
And the paper's conclusion is absolutely stunning. This model, based entirely on vacuum acoustics, doesn't just get close, it perfectly reproduces the properties of a hydrogen atom. We're talking the allowed energy levels, the shapes of the electron orbitals, everything matches the experimental data we've had for decades.
And this slide just shows you the result visually. On the right, these are the known shapes of hydrogen's electron orbitals, calculated by standard quantum mechanics. The shapes predicted by this new acoustic model, on the left, are identical. It's a direct confirmation. The notes of the vacuum perfectly match the steps on the quantum staircase. And if you're a numbers person, here's the hard data from the paper. Just look at that precision. We're talking 9 decimal places. The energy levels predicted by their dynamic vacuum model are an exact match for the observed experimental values for hydrogen. And what's really incredible is that they get this without any special tuning. No fudge factors to make the numbers work. They just calibrate it once to the known mass of the particles, and the entire structure of the atom just emerges. And it's not just energy levels. Get this.
Another fundamental quantum rule, the quantization of angular momentum, also emerges naturally from the model. They didn't have to add it in as a separate rule. It was just a consequence of the concert hall's spherical shape.
Okay, so let's pull back and consider the really big picture here, an emergent universe. If a model like this holds up, what does it mean for how we see reality itself?
So let's just recap the key takeaways. First, quantization, one of the bedrock principles of quantum mechanics, may not be a fundamental rule after all. Instead, it could be an emergent property of this dynamic, fluid-like vacuum. In this new picture, what we call particles are actually creating stable resonances in this vacuum medium. And maybe most profoundly, this whole framework hints at a deeper, underlying reality, one that might just elegantly bridge the gap between the total weirdness of the quantum world and the classical physics of our everyday experience.
And this leaves us with a truly mind-bending thought to end on. We have always been searching for the most fundamental building blocks and the most fundamental rules. But this paper suggests that some of those rules might just be patterns that emerge from a simpler, more unified substrate. So it really makes you wonder, if quantum rules can just emerge, what else about our reality isn't as fundamental as we think?